Okay, afternoon everyone. Are you all able to hear me okay? Is the audio clear enough? Okay, great. I believe you guys have a quiz today for OpenZ 3. Is that right? Yes, I hope you're all prepared. It should be fine if you guys have finished your assignment. Should have no problems. I think it's on the theories of yield. And you have 2-3 hours to complete it. Okay, so this week's tutorial is mostly theory-based because we'll be talking about composite materials. The majority of the concepts taught in composites as well as plasticity is theory-based. So in your final exam, when there are theory questions, most likely they'll come from either this topic or plasticity, possibly FEA, finite element analysis, but for sure, definitely from composites. So we have 5 questions this afternoon, sorry. It's pretty straightforward. So question 1, explain what are the 3 different classifications of composite materials. Now, before we talk about the classifications, can anybody tell me the 3 components of a composite material? Anybody has any idea what are the 3 components of composite materials? So composite materials are made up of the matrix, the bonding agent, which is the bonding agent, the matrix. You have the reinforcing member, and then you have the interface between the two. So those are the 3 major components of composite materials. And those are the 3 components that determine the material properties of said composite. Is everybody in this session part of this session, or are you guys joining from other tutorials? Okay, set, no worries, no worries. Okay, so what are the 3 classifications? First one, particle reinforced. These are further broken down into 2 different groups. We have large particle composites and dispersion strengthened composites. The major difference between these 2 are the size of the reinforcing members. So in the case of large particle composites, as it says in the name, the reinforcing member is large particles. So large particles that are harder, stiffer than the matrix. So majority of the load is taken by the reinforcing member. And the strength of these composites is dictated by the bond between the interface and the matrix. Interfacing bond between the matrix and the reinforcing member. Okay. What that means is basically the transfer of load is efficient when there is a very good bond between the matrix and the reinforcing member. A good example of that is concrete. Okay, we have gravel, which is the reinforcing member, and then you have the cement, which is the matrix. Other examples are concrete with steel reinforcement, all those kind of things. The second type of particle reinforced composites are dispersion strength composites. Major difference between these 2 is the size of the composites. So these generally have very, very small particles, densely compacted and evenly dispersed throughout the matrix. It's similar to precipitation hardening, where it works best with heat. And the way that this works is basically the particles hinder the motion of dislocations. So if there's a dislocation, a crack that propagates, because the the reinforcing members, the particles are so tightly compacted, it can't propagate properly. So, which generally means that plastic deformation is restricted, and this generally improves the yield and tensile strength of the composite. Another major difference between these two is that in dispersion strengthened composites, bulk of the load is taken by the matrix, and for the other, bulk of the load is taken by the reinforcing member. Are you all able to see my my screen, my presentation? Just want to make sure I'm talking and you're all able to see what I'm talking about. Okay, cool. So the second type of classification is fiber reinforced. It's probably the most common one when you think of reinforcing composites. It's basically made up where the reinforcing member is a low density, is a stiff fiber, and the matrix has low density. The strength depends on the fiber length. So the length of the fiber and the orientation of the fiber will determine the strength of the overall composite. And again, the efficiency of the load transfer. So how efficient the composite is depends on the interfacial bond between the reinforcing member and the matrix. And the last classification are structural ones. And these include plywoods and all those kind of things. Generally, strong, stiff end sheets are bonded to a lightweight core. This is the case for honeycomb sheets, also the same for plywood sheets, which plywood sheets are stuck together, different orientations to give it strengths in different planes. So these are the three main classifications, okay? We have particle reinforcements, fiber reinforcements, and structural. Any questions? No questions? Okay, cool. Moving on. Okay, so the matrix, matrix is the bonding member, okay? So in the case of cement or concrete, the matrix is the cement itself, the liquid form that you pour. The reinforcement in that case is the hard gravel or steel reinforcement that you put inside the concrete. Matrix helps to disperse the load, basically. If you want the details of what matrix and all that are, it's all clearly defined in your lecture notes. So I recommend that you guys have a read. Like I said, this topic is majority theory, so a lot of reading. Somewhat like glue, yes, yeah, somewhat like glue, yeah. If you're talking very simple terms, but if you put that in a final exam, the matrix is the glue. I don't think you'll be getting any marks for that. Okay, second question. What is the difference between particle reinforced and fiber reinforced composites? Give an example of each composite. So the major difference between the two, again, as the type of reinforcement that they have. Okay. So for particle reinforcements, it's particles, and for fiber reinforcements, it's fibers. Okay. Major difference is in the name itself. Examples of each: particle reinforcements, concrete, and fiber reinforcements, you got fiberglass and all those kind of things. What are the types of fiber arrangements in fiber reinforced composites, and give advantages and disadvantages of each of the arrangements? So generally, we have three types, okay? We have aligned continuous, or we have continuous aligned members, and discontinuous fiber orientations, okay? So in aligned continuous, we have long fibers, all oriented in the same direction. And the major advantage to this is it has very high strength in the direction that the fibers are oriented, okay? So the fibers are all aligned in the y-axis, so it has very, very strong mechanical properties in that y direction. So it has very high tensile load, very high compressive capabilities in the y direction. However, it is very, very weak in the transverse direction. Okay, so the major advantage is it has high strength, so long as you know the direction of the load and you can align the fibers to that direction of the load, it'll be very, very strong. Major disadvantages that its strength is anisotropic. So anisotropic means it's only got strength in one direction. Isotropic means it has strength in all directions. Okay, and that's the fundamental difference between continuous aligned and continuous unaligned discontinuous. Okay, discontinuous, they have a lot shorter fibers, and the major advantage is that it's anisotropic, meaning it can take a load in all directions, in the y and the x, z, any direction that you load it, it'll be able to take the load. Disadvantage is it's overall weaker in whatever direction you load it. Okay. So if you were to compare this with this side by side, and you were to load them in the y direction, of course, your continuous aligned would be a lot stronger. But then if you were to load them in the transverse, your discontinuous aligned would be stronger. And the last one is the random discontinuous. And this one here has the best anisotropic properties because it has fibers in all different directions. It's all randomly dispersed. Okay. And this is just another example of the differences between continuous aligned and discontinuous aligned, discontinuous random. Is it clear? Any questions from this? Okay. So moving on to question 3. Give 2 examples of structural composites and advantages of using these. So can anybody give me an example of a structural composite material? Cardboard, lumber, yeah, lumber. It depends what type of lumber. Cardboard, yes. Cardboard, yes. Carbon fiber, no, we wouldn't call that a structural composite. Wood, only if it's in the form of plywood or something like that. But yeah, seems most of you guys get the general idea. So structural composites, plastic, not so much. Depends how you what you reinforce it with. If you reinforce it with a fiber like a steel or something, then that is not a structural composite. So stacked and bonded fiber reinforced sheets, that's one example. And the major advantage is its balanced properties in all directions. Now, what do I mean by this? An example of this is plywood. Okay. And when we bond plywood sheets, we often put one in the X, one in the Y, one in the X, one in the Y, all in different orientations. And why do we do that? To give it anisotropic properties, to try and make sure that it's strong in both the X-axis as well as the Y-axis. So plywood is a good example of stacked and bonded structural composite materials. Another one is sandwich panels, which is very similar to cardboard, okay? So it's lightweight and has a large bending stiffness. What do we mean by that? So this is an example of a sandwich panel where it has a very stiff upper surface, stiff bottom surface, and in the middle it's sort of like a core material or a honeycomb. Sometimes it's a foam, sometimes it's corrugated, okay? And the way it works is it kind of works similar to a I-beam, where the top surfaces, where in an I-beam, top surfaces take the brunt of the bending loads, and the middle surface takes the brunt of the shearing loads. Okay, so the major advantages of using sandwich panels is they have very, very high bending stiffness. Okay. Any questions with regards to this? Okay, so question 4. Now, this is one of the few types of questions that you can be asked to calculate when it comes to the composites. Okay. In this question here, we're given a metal composite with wires in it. We're given the volume fraction. So basically the fraction or the amount of the composite that is made up of metal and the amount that is made up of wire. We're given the yield stress and the modulus of elasticity for both. And we're asked to find what is the maximum stress that the composite can carry without yielding. Now, let me just ask you a question. Or no, let me pose it to you this way, okay? What's the whole purpose of making a composite? What's the desired goal of having a composite? Why would we use a composite instead of just a pure alloy, or not pure alloy, a pure metal? Any ideas? To have high strength at low cost, material that possesses high strength but at low weight. These are all, yes. Okay, thank you, Bamba. It's to improve the properties, okay? All of your answers are correct, but they're all very specific. This is the most appropriate answer. They're to improve the mechanical properties of the materials on their own. And what we're doing essentially is we're combining two separate materials and making them one. Okay, so if you understand that, then you'll be able to understand the condition of compatibility, which basically states that the strain experienced by the wire will be the same thing that is the same strain that is experienced by the matrix, because they are one material. The material will deform the same, both in the matrix and in the wire. Okay, that's one of the main concepts to grasp when you talk about composites, that there is a compatibility condition. The strain experienced by the wire will be the same strain that's experienced by the matrix. But, and this is where the but comes in, the stresses experienced by both will not be the same, because the majority of the stress should be carried by the stronger material, yes? But we are bonding it in a composite form with a weaker material, maybe to improve certain properties, or to share the load that is to be experienced by one. So first thing you have to state is the condition of compatibility. So essentially, the strain in the wire should be equal to the strain in the matrix. And strain, as you know, is the ratio of stress and Young's modulus. And we are given the stress and the Young's modulus for both. So using those, we can then calculate the strains in each of our materials. So we can calculate the strain in the wire and the strain in the matrix. Clear up to this point? Okay, great. So now begs the question, which one of these two strains will we use will govern the design of our composite, will limit the abilities of our composite? Which one do you think is the more critical strain to consider? The smaller one. And why do you say that, Knight? Why do you think the smaller one is more critical? You are correct. It is the smaller one. The reason that we say it's the smaller one is because if we were to try and stretch this element by this amount, it would fail, basically. Okay, so this material, our matrix, can beat this strain value, no problem. But if we try and strain the wire to the amount that the matrix can take, it would fail. So we will take the smaller one as the composite yield. Okay, the composite will yield at the lower strain. Now, knowing that bit of information, when the wire has a strain of 0.0084, the stress in the material will be 210 megapascals. Now we have to find at this strain, how much stress will there be inside the matrix? So we basically take the strain, multiply it by the Young's modulus, and we get the stress in the matrix M. And now we can apply the formula that is given in your notes, where it's basically the maximum stress that the composite can take is equal to the maximum stress of the wire times the volume fraction plus the maximum stress of the matrix times the volume fraction. Volume fraction is 50%, so that means 50% for both. If we run that calculation, maximum stress will be equal to 210 times 0.5 plus 37.8 times 0.5. And we have a maximum stress that our composite can take at 123.9 megapascals. Okay. And then if we go back to my original question, why do we make composites? To improve the material properties. Our matrix is 70. 70 is the maximum. We have now increased it to 123 by adding a 50% reinforcing member in the form of the wire. This is how you tackle these kinds of problems if they were to come up in a short test or exam. Any questions? So as of this week, you guys had to submit your tutorials for this week. So these tutorials, you had to submit them before the week started so that you could get attendance. Did you all manage to do that? I know it's a bit of a task since you guys had to finish your assignment. You have a new assignment out, you have lab reports to do, as well as other units that you have to worry about. But unfortunately, that's the most effective way that we can keep track of attendance going forward that Mr. J. Gounder has decided on. So you guys just have to make a sincere attempt. You don't have to get it all right. They won't be marked like an assessment or a test or anything. You just have to show that you've attempted. Okay. Last question. What are fiber reinforced polymers and what are the advantages and disadvantages of using fiber reinforced polymers? It is basically a polymer matrix embedded with high strength fibers. Polymer materials are usually thermosetting plastics, but also can be thermoplastic. And the laminar structure is the most widely used form for fiber reinforced polymers. The advantages: it has a high strength to weight ratio, high modulus of weight ratio, modulus to weight ratio, low specific gravity, which means low density, good fatigue strength, good corrosion resistance, and low thermal expansion. Major disadvantage is it's very expensive, and generally they are anisotropic, so only able to be loaded in one direction effectively. Okay guys, that brings us to the end of our 5 questions for this week. Do you have any questions before we end the session regarding the lab reports or the questions that we covered today? Any questions? If you have a question, you can unmute your mic and ask. Yes, for lab report. Hold on, let me just bring up the lab report format. Okay, hold on. Let me just share this. Okay, can you all see my screen? So the procedure step is pretty self-explanatory. You guys just have to talk about the procedure that you took to simulate your experiment and the reasons for each of the steps. The modeling and or design, you just talk about the boundary conditions that we applied, okay? That's the most important thing probably from this experiment. If you remember, we applied symmetry boundary conditions. Okay, and that is possibly one of the most useful things to take away from this lab experiment is the importance or the use of applying symmetry boundary conditions. So in this section, you can talk about why we had to apply a symmetrical boundary condition, what was the reasoning behind it, and what was the end result of applying a symmetrical boundary condition. Okay. You may also talk about how you extracted the certain coordinates to enter or your geometry, but that's not really necessary. The most important thing that you can talk about here is the symmetrical boundary conditions. You may also talk about why we did it as a plane stress analysis problem, meaning two-dimensional. Why did we analyze it as two-dimensional? Why did we select the element that we used? I think it was 189. Why did we use that element? I don't know if there were any warnings that popped up that said that we were using triangular elements. If that did come up, that comes in your solution accuracy and errors section. Okay. Does that help answer your question? Okay, great. If there are no more questions, thank you very much for attending today. And all the best for your quiz later today. If you have any questions over the weekend about anything, please feel free to let me know. If that's all, thank you very much, and I will see you guys next week. Naka.